So welcome you to today's lecture. If any one of you have any doubts from the previous lecture or the last lecture, feel free to ask any of your doubts. So if there are no doubts, let me proceed with my next topic. So if you recall, in last lecture, I had started with the concept of unbiased estimation, which is not new to you because you have done a lot of it already at your bachelor's level. In fact, a lot of things you might have already done at the bachelor's level. So it would be a quick review of what you did at the bachelor's level, but slightly the level of problems may be slightly at advanced level than what you did at bachelor's level. So let me just share my notes. So if you recall, I was dealing with this so-called unbiased estimation. And I said that if you have to look at any estimator, its performance has to be evaluated through its risk function, which is the expected or the average loss of an estimator delta, when theta is the true value of the parameter. I also call that as saying when theta is the true state of nature. Now this measures the preciseness with which delta estimates psi theta. Since L is a loss function, I would like to have risk small as possible. So one would like to choose delta that minimizes the risk for all values of theta belonging to theta. So best scenario would be a scenario where I can find an estimator for which this risk is minimum, whatever theta may be. Now, unfortunately, that doesn't happen because let us look at an estimator. Let us look at an estimator delta naught x, which is theta naught. Theta naught is a fixed quantity. Theta naught is a fixed quantity. Of course, this would belong to the parameter space, a fixed quantity in capital theta. All right. So this estimator is a very funny estimator. In fact, in practice, nobody would like to use this estimator. Why? Because it says, irrespective of what your observation is, you always estimate theta by theta naught, which is a fixed constant. So you're not going to see the data at all. You would say your estimate is theta naught. Now let's look at what is the performance of this estimator. When I look at L theta delta x, because delta x is always theta naught, so if your loss function is squared error, theta minus theta naught whole square, under squared error loss function. Otherwise, it would be L theta delta naught. So the loss function is theta minus theta naught square. So if I look at L theta naught delta naught x, this is always 0. Whatever observation x may be for every x. If a function is constant and its expected value, which is r theta naught, risk at point theta naught of an estimator delta naught would be E theta naught of L of theta naught delta naught x, which is 0. So what it says, risk of the estimated delta naught at theta naught is 0, which would be certainly smaller than risk of any estimator at point theta naught. Any estimated delta, which is basically expected value of delta x minus theta naught whole square. Why? Because this is non-negative. So this quantity would be less than, this would be 0 only when. This can be 0 only when, because this is already 0. So this would be 0. So the only possible quantity is when this is 0. Now this would be 0 only when probability that delta x is equal to theta naught is 1, because this is square error. Unless probability that delta x is equal to theta naught is 1, which is same as this estimator. So any estimator which is different from delta naught would have a smaller risk than this funny or constant estimator theta naught. So this suggests that irrespective of what you do, minimizing the risk at particular points may not be possible, because if you're just interested in minimizing the risk at a particular point, this constant estimator would minimize the risk. Now, such estimators are called locally optimal. Locally optimal means they only minimize the risk locally, only at one point, locally. So this discussion suggests that if you're considering all the estimators at your disposal, then it may not be possible to minimize risk at every theta. And the reason is that these constant estimators are troublemakers. But these constant estimators are nuisance, right? Why one would like to consider such estimators? So what one can do is, one can restrict the class of estimators under consideration by getting rid of estimators like these constant estimators. And how one can do is, one can say that, look, I'll impose certain reasonable restrictions on the estimators to be considered. And then I consider only those estimators. And among these reasonable estimators, I try to find the best estimator. So this is what the discussion says, that there exists no uniformly best estimator. That is, no estimator exists which minimizes the risk for all values of theta, except in trivial case that psi theta is constant. Your estimate itself is constant, known. Now, one way to avoid this difficulty is to restrict the class of estimators by ruling out estimators which do not possess certain desirable characteristics. And one such desirable characteristic is the unbiasedness. So I say that an estimator delta x is unbiased if on an average, its value is psi theta. What it means is, recall that I have said that an estimator is a rule. So what this says from the applied point of view is, as a rule, if you use delta x over an extended period of time on different occasions you take different sample and you calculate delta as a rule. Then on an average, it will give the same value as the thing which you're trying to estimate, psi theta, and which is a very desirable property. On an average, it should give the same psi theta. Now, if there exists an unbiased estimator of psi, the estimand will be called U estimable. So I'll say that an estimator is U estimable if and only if an unbiased estimator for it exists. Now, unfortunately, unbiased estimators may not always exist. So for example, if you look at the binomial and theta case and is a known positive integer, then unbiased estimator for 1 by theta does not exist. And the proof is very simple. So on contrary, let delta be such that, so that means I am contrary, I'm assuming that there is an unbiased estimator, such that expected value of delta x is 1 by theta for every theta belonging to 0, 1. What does that mean? Expected delta x is summation j is equal to 0 to n delta j, and choose j theta to the power j 1 minus theta to the power n minus j is same as 1 by theta for every theta. So I can make this as summation j is equal to 0 to n delta j and choose j. I can make this as theta upon 1 minus theta to power j. And 1 minus theta to the power minus n I can take over there. So 1 minus theta to the power minus n by theta. So this happens for every theta belonging to 0 and 1. Now I can make the transformation that theta upon 1 minus theta as, let us say, y. So that means theta becomes y upon 1 plus y. Right? Of course, theta can take any values between 0 to 1, and theta upon 1 by theta is an increasing function. So this can take any value, and it is a continuous function, so it can take any value between 0 to infinity. Right? Because theta is equal to 0, it is because it is an increasing function of a theta. You can take the derivative and see it is an increasing function of theta. So its minimum value would be when theta is equal to 0, which is 0, and theta is equal to 1, it is infinity. And it is a continuous function, so it will take all values between 0 to infinity. So y takes between 0 to infinity. So what it means is, this would mean that summation j is equal to 0 to n delta j and choose j y to power j is same as 1 minus theta to power minus n. 1 minus theta is nothing but 1 upon 1 plus y, right? And that becomes 1 by y to power n, I guess. Right? 1 minus theta is 1 upon 1 plus y, so 1 plus y to power minus 1, and 1. And then theta is y upon 1 plus y, so divided by y into 1 plus y, or y between 0 to infinity. Now note that this you can write down as a polynomial. So this I can take over here. Summation j is equal to 0 to n delta j, and choose j y to power j plus 1 is same as, then I calculate this. I can expand this, so 1 plus y. Summation j is equal to 0 to n, and choose j y to power j, which basically becomes, if you want to do it, summation j is equal to 0 to n, and choose j y to power j plus summation j is equal to 1 to j is equal to 0 to n, and choose j y to power j plus 1. This you can write down as summation j is equal to 0 to n, and choose j y to power j. And here j plus 1, it's starting from j plus 1. So here you can start j is equal to 1 to n plus 1. And it would be n choose j minus 1 into y to power j. So this becomes summation j is equal to 0 to n choose j plus n choose j minus 1 into y to power j. Now both the sides you have a polynomial in degree of y, right? So their coefficients have to match. There would be n plus 1 term also. So n choose n plus y to power n. So this would be, let me just see, j is equal to 0 term would be separate. J is equal to 1 to n, you can combine. And j is equal to 0 would be 1 plus j is equal to n plus 1. Here it would be n choose n y to power n plus 1. So you can see you have a polynomial of degree n both the sides. There's a y to power n plus 1 over here. There's a y to power, so all coefficients would match. And you see, if you match that coefficients, you'll not get an estimator which is unbiased. For example, if you have to see what is the coefficient of y to power 0? Y to power 0 coefficient on the left hand side is 0. On the right hand side, y to power 0 coefficient is 1. So 0 is equal to 1 cannot happen. So this will never hold, right? So such a delta will not exist, because if such an estimated delta exists, then you get a power series on both the sides. When you start comparing the coefficients, you see that can never happen. Now, similarly, unbiased estimator of e to power minus theta does not exist in the Poisson case, because if it exists, then what do you have? Then you have summation j is equal to 0 to infinity delta j, and it is Poisson theta, so e to power minus theta to the power j by factorial j is same as e to power minus 3 theta for every theta greater than 0. This e to power minus theta you can take outside that side, so it becomes j is equal to 0 to infinity delta j theta to power j by factorial j, and it becomes e to power minus 2 theta. And what is e to power minus 2 theta? Summation j is equal to 0 to infinity minus 2 to power j theta to power j by factorial j. Now, if you compare the coefficients of theta to power j on the both sides, you get delta j upon factorial j is same as minus 2 to power j by factorial j, which gives me delta j as minus 2 to power j. So here such an estimator exists, which is minus 2 to power j. But the funny thing with this is your theta takes only positive values, whereas this delta can take positive as well as negative values. So there is an issue with this. You see, unbiased estimator in the first case does not exist. One have done is this way. If there is some smart person, he may directly conclude that unbiased estimator in the binomial case does not exist, because you have two sides, left hand side a function of a theta, right hand side a function of theta. Both the side it is a continuous function of theta. So if it is happening for every theta belonging to 0, 1, it should happen in the limit also. So limit theta going to 0 as well as 1 of left hand side should be same as theta going to 0 or 1 of right hand side, because both are continuous functions. So when I look at theta going to 0 on both left hand side, where does it goes to? It will go to delta of 0, because theta upon 1 minus theta power 0 will not contribute. Rest of the term theta will come and they will contribute 0. So this would be delta 0 when I take theta is equal to 0 on the left hand side. What is the theta going to 0 on the right hand side? Theta going to 0, this is 1, and this becomes infinity. So you cannot get any estimators as that delta 0 is equal to infinity. So such a thing can never hold. You can take theta going to 1 also. If you take theta going to 1, then all the terms are infinity, except j is equal to 0 term. And when you take theta is equal to 1 over here, here also you get infinity. So that is not an issue. But delta going to 0 is a problem. As theta goes to 0, left hand side is delta 0. What is the right hand side as theta goes to 0? Infinity. So such an estimator will never exist. So I gave these two examples where in the first case, the unbiased estimator does not exist. I have shown it in two ways. One, you can smartly see as theta goes in limit to 0, this cannot be satisfied, which had to be satisfied because both are continuous functions on left hand side and right hand side. Other ways, you do it through brute force, which again gives you a problem in terms of comparing the coefficient of y to power 0 on both sides. Here you get delta 0. Here you don't get anything because there is no term of y to power 0, and here y to power 0 is 1. So there is an issue. So they cannot match. because if they have to match, the coefficient had to match. So now what we have done is we have restricted the class of estimators to be the class of unbiased estimators, and we try to find out the best estimators over there. Now note that I have put a desirable condition as the unbiasedness. That means my estimators should be unbiased, and I'm trying to find the best estimators among unbiased estimators. Now sometimes what may happen is, if you are willing to sacrifice a little bit on bias, it may be possible to get estimators which have a smaller risk function, much smaller risk function. So there's a trade-off between your unbiasedness and the risk function. So after a best unbiased estimator, the estimator having uniformly smallest risk among all unbiased estimators has been found, its performance should be studied to find out if there exists a slightly biased estimator which may not be unbiased and which is beyond your consideration. That's the reason. So there's a possibility that a slightly biased estimator with uniformly much smaller risk may exist. And one should not rule out there's such a possibility. So what is being suggested through this remark is, after you have found the best unbiased estimator, that means the unbiased estimator having the smallest risk, you should try to look at other estimators, and there's a possibility that there may be one estimator, there may be some estimators which are slightly biased, but you did not consider them because you're considering only unbiased estimators. But these biased estimators may have very smaller risk, much smaller risk than the biased estimator which you are considering. So one has to keep an open mind. One should not stop just with unbiased estimation. After finding the best unbiased estimators, you should also try to look around and see if there exists an estimator with slight bias, but much smaller mean squared error, or the risk function. Let us go further in our attempt to find the best unbiased estimator. So my estimate is psi theta. The quantity I want to estimate. Let D, script D, be the class of all estimators of psi theta. D0 is the class of all unbiased estimators of psi theta. That means collection of all those data belonging to D, such that expected value of delta X is psi theta. So D0 is the class of all unbiased estimators of psi theta. Let us denote U to be the class of all unbiased estimators of 0. So what is U? Is the class of all unbiased estimators of 0. That means collection of all those U belonging to D, such that expected value of U is 0. This need not be D, it can be anything. You can simply say the collection of all those U's such that expected value of Ux is 0. So first, what I do is I try to characterize the class of all unbiased estimators. So what it says is this lemma. Suppose I know one unbiased estimator, call that as delta naught. So let delta naught be an unbiased estimator, be fixed. So this is known to me. Then I can get all other estimators, all other unbiased estimators through delta naught by this. Then D naught, which is the class of all unbiased estimators, is collection of all those delta, says that delta is delta naught minus Ux for some unbiased estimator of 0. So this tells you, given just one estimator, which is unbiased for psi theta, you can get the class of all unbiased estimators, or you can characterize the class of all unbiased estimators of theta through this. So any delta would be nothing but this estimator which you have fixed minus an unbiased estimator of 0. The proof is not difficult. So first, I prove that this is a class of all unbiased estimator. That means what I have to show? That first I prove that delta belongs to right hand side. That means delta is of this type. Then I have to show that it is unbiased. Okay? This implies, because I have to show that then delta belongs to D naught. I have to show that these two sets are same. And you know from your school mathematics, when you show that when you have to show that two sets are same, what do? You take an element of one, so the element, it belongs to the other set. Take the element of the other set, try to show that it belongs to the other. So that is what I'm saying. Suppose delta belongs to the right-hand set. This implies that delta is same as delta naught x minus ux for some u, which is unbiased for 0. What does that mean? That means expected value of delta x would be expected value of delta naught x minus expected value ux, but u is belonging to unbiased class of unbiased estimator of 0, so that would be 0. So this is expected value delta naught x. But my delta naught was fixed, and it is an unbiased estimator of psi theta, so it is same as psi theta. So this says that delta would be an unbiased estimator of psi theta for every theta, which says that delta belongs to D0. So that means right-hand side is contained in D0. Now I have to show that any D0 belongs to this. Let delta belongs to D0. Then I have to show that delta can be written as delta naught minus unbiased estimator of 0. So what I do is then delta x can be written as delta naught x minus delta naught x minus delta x. I've just added and subtracted delta x. So this is delta naught x, and I can call this as ux. So my delta x is same as delta naught x minus ux. The only thing, so that means it is of this type. The only thing I have to show that ux belongs to u. That means this u is unbiased for 0. So expected value of ux is same as expected value of delta naught x minus delta x. Expected delta naught x by my choice was fixed and unbiased for psi tau theta. So this is anyway tau theta. And delta had taken to be an element of D0 that is unbiased for tau theta. So this would also be tau theta. So it's the same. So my delta x is same as delta naught x minus some function of x which is unbiased for 0. So that means my delta belongs to the right-hand side. So this implies that delta belongs to the right-hand side. And you are done. So this helps us in characterizing all the unbiased estimators of the estimate tau theta. How it is that?
Why is the second part of the statistics, I mean the expectation of, why is this 0?
You see, let us look at the hypothesis. My original hypothesis says my delta naught is a fixed estimator, fixed unbiased estimator of D naught, right? And this class, right-hand side class, has been constructed using this whatever was fixed to. For example, in the normal theta 1, it would be x bar. Right? So what I'm trying to show is left-hand side is contained in right-hand side and right-hand side is contained in left-hand side. Right? First part is okay. That
Yes, sir.
Now let us look at, I take an element of the left-hand side. That means delta belongs to D naught. Delta belongs to D naught. That means delta is unbiased for tau theta. That I know. Right? Because that is a definition of D naught is a class of unbiased estimators of tau theta. Right? Now then I can write down, so I have to show that delta belongs to this set. For delta belong to this set, I should be in a position to write down delta as delta naught minus some ux, which is unbiased for 0. So I write down delta x as delta naught x minus delta naught x minus delta x. And I call this as ux. So that delta x is delta naught x minus ux. It will belong to this set provided u is unbiased for 0. So I look at whether this is unbiased for 0 or not. So when I look at expected value of ux, it is same as expected value of delta naught x minus expected value of delta x. What is expected value of delta naught x? By choice, my delta naught was belonging to D naught. It is unbiased for tau theta because that is a definition of a delta naught. So it is tau theta. And what was delta? Delta anyway I had taken to be an unbiased estimator of D0 because I'm trying to show that if delta belongs to D0, then delta would be of this type. That means if delta is unbiased, then it would be of this type. So this is also tau theta. Because both are delta 0 and delta are both unbiased for tau theta, and which is 0. So that means my delta x can be written as delta naught x minus ux, and ux is such that expected of ux is 0. So that means delta is of this type.
Sir, was this psi theta or tau theta?
Tau theta, it is all, tau theta is the estimate. The quantity I'm trying to estimate, right? Estimate is tau theta. So in my problem, I'm interested in estimating, sorry, tau theta I can put. Yeah, I'm sorry for this mess up. Let me put here tau theta. Is that okay? Whatever is the estimate, that is this quantity. Is that okay?
Okay, sir.
Now let us look at the problem of finding unbiased estimators, UMV estimators, uniformly minimum variance unbiased estimators. So consider the squared error loss function L theta D, which is psi theta minus D whole square. Psi theta. So again, there is some mess up of psi theta is the estimate. Here. Quantity you want to estimate. Now, for any unbiased estimator, so for any delta belonging to D naught, what is the risk function? It is expected of delta x minus psi theta whole square, which is expected value of delta x. Psi theta, because your delta is unbiased, it will be same as expected value of delta x whole square, which is variance of data. So for any unbiased estimator, if your loss function is the square error loss function, then the risk is same as variance. This is true only for the unbiased estimator. So where V theta D denotes the variance of data. Thus finding an estimated delta star in D naught, that is among the all unbiased estimators, that has the smallest risk among all estimators in D naught, is equivalent to finding an estimator in D naught that has the smallest variance. Now note that here I have only considered the non-randomized estimators. This is very important. Note that here we may consider only non-randomized estimator. Why? Because I'm considering the squared error loss function, which is convex. This is convex in T. Because its double derivative with respect to D is always positive. And you know that if you have a convex function, then it is enough to consider estimators which are non-randomized. And that is what is happening over here. So anywhere where you have a convex loss function, there is no need to consider randomized estimators due to the result which we did in one of the earlier lectures that given any randomized estimator, you can find an estimator which is non-randomized and which has a smaller risk than the given randomized estimator. And use the Jensen's inequality to do that, provided your loss function is convex. So that's the reason here I'm not considering the randomized estimators, I'm only considering non-randomized estimator. So this leads to the definition of a minimum variance unbiased estimator. An estimator delta star belonging to the class of all unbiased estimators is said to be, first I give the definition of a locally minimum variance unbiased estimator. That means it has the smallest variance locally. Locally means only at a fixed point. So an estimated delta star belonging to delta naught, D naught is said to be locally minimum variance unbiased estimator, which we denote by LMVU, estimator at theta naught. If for any unbiased estimator, variance of delta star at the point theta naught is smaller than variance of delta naught at the point theta naught. This would be data if for any other data. So that means locally minimum variance unbiased estimator minimizes the risk or the variance only at a fixed point theta naught. And that is why we say it is locally minimum variance unbiased estimator at point theta naught. I can talk about an estimator which is uniformly minimum variance unbiased estimator. That means it is locally minimum variance unbiased estimator at every point theta. So an estimated delta star is said to be uniformly minimum variance unbiased estimator. If for any unbiased estimator data, so for any data belonging to V naught, variance of delta star is less than or equal to variance of delta, now not locally, but for every theta. So there's a concept of a locally minimum variance, there's a concept of a uniformly minimum variance. So let us try to see how do I find the uniformly minimum variance unbiased estimator. Now let delta naught be a fixed unbiased estimator. It could be like X bar in the normal case. Then I know that any unbiased estimator can be written as delta naught X minus UX for some unbiased estimator U of 0. Now if that happens, let us look at what is the variance of delta. I'm trying to minimize the variance of delta. Now my delta naught is fixed. It would be X bar. So I'm trying to see what is the variance of delta, this arbitrary estimated delta in terms of variance of delta naught and UX. So it is same as variance of delta naught minus U. So I look at this is same as expected value of delta naught minus U minus psi theta whole square, which is same as I square it and then do it to expected delta naught minus UX whole square. Then it will be plus psi theta. So it will be minus 2 times psi theta into expected value of delta naught X minus UX. But delta naught, so this, if you want one more step, this would be same as expected value of delta naught X minus UX whole square minus 2 psi theta expected value of delta naught X minus UX plus psi square theta. Right? Now note that delta naught is unbiased for psi theta. So it will be expected delta naught, which is psi theta, and U is unbiased for 0. So it will be just psi theta. So it is minus 2 psi square theta plus psi square theta. That makes it minus psi theta. So this is exactly this. So I have to minimize this with respect to delta. That means I have to find a delta for which this is minimum. But delta is varying because delta naught is fixed. So delta is varying only through the choice of U. So in other words, I have to find a U for which this quantity is minimum. Note that psi theta is estimate, which is a fixed quantity, does not depend on U. So that means finding an UMVE is equivalent to finding U for which this quantity is minimum. For a fixed delta naught, which was given to you. We started with fixed delta naught. It could be X bar in the normal case, as I said. So thus to find the locally minimum variance unbiased estimator at theta naught, it is enough to find a U star, which is unbiased for 0, such that this quantity is minimum. So such that expected value of delta naught U star X is less than or equal to expected delta naught X minus UX whole square for every U belonging to U. So that means if your delta naught is fixed, you try to find out an estimator for which this quantity is minimum. Just find an unbiased estimator of 0 for which this quantity is minimum. So let's try to see an implementation of this observation. So suppose that X has a PMF, F theta K, which is theta, if K is equal to minus 1 minus theta square theta power K is equal to 0, 1, 2, 3, 0, otherwise. And suppose my estimates are 2, I'll consider them separately, psi 1 theta as theta and psi 2 theta as theta square. Find the uniformly minimum variance estimators of psi 1 theta and psi 2 theta, provided they exist. Now note that the previous discussion has said that if you have to find a minimum variance unbiased estimator of psi theta, start with an unbiased estimator of psi theta, call it as delta naught, and then try to minimize or try to find U such that expected delta naught X minus UX whole square is minimum among all unbiased estimators of theta, or among all unbiased estimators of 0. Find such a U. And then delta naught minus U star would be the given minimum variance unbiased estimator or locally minimum variance unbiased estimator, as the case may be. So first, let us try to find out. So irrespective of what happens, you have to find out first, how does an unbiased estimator of 0 looks like in any problem, whether you're estimating psi1 theta and psi2 theta. Unbiased estimator of 0 have nothing to do with psi1 theta or psi2 theta. They are just unbiased estimator of 0. So first I try to look at how does an unbiased estimator of 0 looks like. Then I can come to these problems separately, because a characterization of unbiased estimator of 0 would be required for both the problems, whether you're estimating theta or theta squared. Now it can be shown that an estimator of 0 would have this type, would be of this type. UK would be same as minus k times u minus 1, and UK would be same as a times k for some constant a belonging to R. So any unbiased estimator of 0 would be of the type a times x. UK is a times k. So that means any unbiased estimator would be of the type, any unbiased estimator of 0 would be of type a times x. How do you prove it? That is very simple. It is again comparing those coefficients. So let me just see. You have to look at expected u belongs to u0. If and only if expected value of ux is 0, right? For every theta belonging to 0, 1. I look at expected value of ux over here. K is equal to minus 1 with probability theta. So u of minus 1 into theta. Plus, now summation k is equal to 0 to infinity uk into 1 minus theta square, theta power k is 0, or every 0 less than theta less than 1. 1 minus theta power minus 1 I can take over here, so it becomes v to power minus 1 theta into 1 minus theta to power minus 2 plus summation k is equal to 0 to infinity uk theta to power k is 0 for every theta 0. I can expand this, so the same as u to power minus theta, and then 1 plus 2 theta plus 3 theta square plus 4 theta cube, and so on, the same as summation k is equal to 0 infinity uk theta to power k for every theta. This becomes u to power minus theta plus 2 theta square, so that becomes u to power minus 1. Summation k is equal to 1 to infinity k theta to power k plus summation k is equal to 0 to infinity uk theta to power k. You see? So what it happens? You can start comparing the coefficients on both the sides because you have power series. So what is the coefficient of theta to power minus 1? There is no coefficient. Theta to power 0. Theta to power 0 only comes from here. So that means u0 is 0. And then for k is equal to 1 to infinity, coefficient of theta to power k comes from the both sides. So uk, and what is the coefficient of theta to power k over here? K times u minus 1. K times u minus 1. You see? So that means UK, any unbiased estimator would be of the type UK is equal to minus K times U minus 1. K is equal to 0 anyway, it is satisfied. So minus K times U times minus 1. Right? And you can keep U of minus 1 as, let us say, minus A, then it becomes UK as same as A times K, right? And K is equal to minus 1, it is always satisfied. So UK would be of the type A times K. So any unbiased estimator, you would be unbiased if and only if ux is same as a times x. A may vary. As A varies, your U varies. So there is not one unbiased estimator of 0. There is a class of unbiased estimator of 0. And any unbiased estimator of 0 looks like of the type A times x. So let us consider estimation of psi theta. So note that what I have to do. I have to first find an unbiased estimator of estimate. The class of all unbiased estimator vary like delta naught minus ux. And then among them, you try to find out one which minimizes respect to delta naught x minus ux whole square. So first I try to fix an unbiased estimator of theta. Note that here my PMF is like this. So if I take my UK to be 1, if k is equal to -1 and 0 otherwise, then it would be u of -1, which is 1 into theta plus others are 0. So it will give me an unbiased estimator of theta. So this tells me how to get an unbiased estimator of theta, and which I get delta naught x as 1 if x equal to -1, 0 otherwise. And this is an unbiased estimator of theta. The way the PDF is written over here, delta of -1 into theta. And delta of -1 I have taken to be 1. So that is theta. Any other unbiased estimator would be of the type delta naught x minus ux, which is delta naught x minus ux. What I have to minimize? We want to minimize for any fixed theta naught belonging to theta, h1a, which is delta naught x minus ux whole square, which is minus ax whole square. And only way your u's are varying is only through a. So I try to find out a which minimizes this. And that is why I have kept this as a function of a. Then I can get an unbiased estimator of 0. Suppose this is minimized at a star, then a star x would be the unbiased estimator of 0, which minimizes delta naught x minus ux whole square. So just try to see what it is. This is what is your delta naught x? Delta naught x is x equal to -1. So first I look at x equal to -1. It is -1 minus x equal to -1. -1 plus delta naught -1 is 1. And this becomes plus a, x equal to -1 plus a with probability theta naught, because I'm calculating the risk at theta naught. So that would be 1 plus a square into theta naught. 1 plus a square into theta naught is this theta naught comes outside, twice a theta naught comes outside, and a was -1. So this is actually, if you want, you can write down as first I start with delta naught -1 minus x equal to -1, it gives me plus a whole square into what is the probability x equal to -1? Because I'm calculating the risk at theta naught, probability x equal to -1 is theta naught. Risk at theta naught. Then plus summation k is equal to 0 to infinity. Delta naught k minus a times k whole square. And then this quantity, probability x equal to k, which is 1 minus theta square into theta. And of course, this would be at everything at theta naught because I'm calculating the risk. Delta naught of -1, the way I have chosen my unbiased estimator is delta naught of -1 is 1. So this is 1 plus a whole square into theta naught plus. For k is equal to 0 onwards, delta naught is 0. So this is same as summation a square. Summation k is equal to 0 to infinity. K square into 1 minus theta naught square, and theta naught equal k is 1. And this is exactly this quantity is. 1 plus a square, I have broken it into 2a comes over here. I have collected all the terms of a square. So which is theta naught plus 1 minus theta naught square. Summation k is equal to 0 to infinity. K square theta naught to power k and a square plus 2a theta naught plus theta. Now, if you try to minimize this, I see the double derivative is this quantity, which is always positive. So wherever the derivative is 0 will give you a minimum, and derivative is 0 is minimum at this point. So if I have to find the locally minimum variance unbiased estimator, the best choice I get is minus theta naught upon 1 theta naught plus 1 minus theta naught whole square. Now this theta naught, this choice of a star which minimizes this delta naught x minus ax whole square depends on at what point I'm trying to minimize the variance. So that means as you keep on changing this point theta naught, your minimizing a star would keep changing. So there is no single theta, there is no single a star which works for all theta because it is only locally minimizing at theta naught. So if you have to, if you're interested in only minimizing the risk locally at theta naught, then it says you consider delta naught x minus a star. A star is given by this. But you have to minimize the risk for every theta naught. So this, since this a star is depending on theta naught, this estimator will keep changing. So locally minimum variance unbiased estimators would keep changing, and you would not have a single estimator which is locally minimum variance unbiased estimator at all theta. And that is why, because the reason is because this a star depends on theta. So in this case, I can say that no uniformly minimum variance unbiased estimator exists. So thus delta star x, which is delta naught minus a star x, is the locally minimum variance unbiased estimator of psi theta at theta is equal to theta naught. Since a star depends on theta is equal to theta naught, and a star is the unique minimizer, we conclude that no UMUE of psi theta exists. So even when unbiased estimators exist, the uniformly minimum variance unbiased estimator may not exist. This is one such example. Now let's consider another example where you're interested in finding an unbiased, estimating psi to theta, 1 minus theta whole square. So the first thing which I have to do is I have to determine delta naught x. That means I have to fix one estimator which is unbiased for 1 minus theta whole square. For this, again, I try to look at the PDF. PDF of this. Note that when k is 0, only 1 minus theta square is coming. So it looks like if I take my estimator delta naught to be 1, if k is equal to 0 and 0 otherwise, then the only thing which will contribute is u of k, which is 1, into the corresponding probability, which is 1 minus theta square, 1 minus theta square, plus rest of the places anyway uk is 0. So in the expectation, they will contribute 0, and you'll get 1 minus theta square. So I can guess in this case what is my unbiased estimator, one unbiased estimator of psi theta, which is 1 if x equal to 0, 0 otherwise. Then delta 1 is an unbiased estimator of 1 minus theta whole square. So thus delta belongs to G0 if and only if delta is of the type delta 1 minus ux, where ux is any unbiased estimator of 0. And you know that any unbiased estimator of 0 is of this type, a times x. What I have to do in this case, I have to find a which minimizes delta 1x minus ax whole square. A fixed estimator which I have chosen to begin with, minus unbiased estimator ux whole square. As you vary u, which is equivalent to saying that as I vary e. I again do that. This is nothing but delta 1 of minus 1. X equal to minus 1 is plus a whole square. X equal to minus 1 probability is theta plus summation k is equal to 0 to infinity. Delta 1 k minus a times k whole square. 1 minus theta square and theta power k, because I'm calculating everything at theta 0. So which is same as delta of -1. Delta is 1 only when x equal to 0. So it would be, otherwise it is 0. So this is a square theta naught plus 1 minus theta naught whole square. K is equal to 0. This is 1, right? Delta 1, 0 is 1. So this is 1. And K is equal to 0. You get 1 minus theta naught square. That is what you get over here. And then, so you get only 1 plus summation K is equal to 1 to infinity. Then delta 1 K is 0. So a square, K square, theta naught. And that is what exactly you have written down. So again, I have to minimize this respect to A. Note that there is no A over here. So what is the minimizing A? Only when A square is 0. A square is 0, that means A is 0. So clearly B star is equal to 0 minimizes H2A, and it is a unique minimizer. So in this case, the minimizer does not depend on theta naught. B star does not depend on theta naught. So it follows that the locally minimum variance unbiased estimator, which is locally minimum variance unbiased estimator at any theta naught you choose, because the minimizer B star does not depend on theta. So that becomes UMVE. So UMVE is nothing but delta 1x minus 0, because minimizer is 0. B star into 0. So delta 1x is the UMVE of psi 2 3. So what we gain from the last example is even restricting to unbiased estimators may not ensure existence of the best unbiased estimator. So there may be situations where this doesn't hold, but in a lot of situations, we'll see that if you restrict to the class of unbiased estimators, you can find the best estimator. So let me stop over here today. We'll continue from here in the next lecture. I'll be uploading a new homework today, which would be based on the last module. I'll try to upload solutions of the last assignment, which was on Basu's theorem. That also I try to do today. So this is all from my side for today. If you have any questions, you may stay back. Others may leave if you want. If you want to stay back, perfectly fine. Just stay back for any doubts you might have. Okay, Rosen, do you have any questions? Rosen? Okay, it looks like Rosen, you're not here. You just came, logged in, and then you just vanished. Okay, so let me just call off the meeting.